Example 4 in Stat 101, examples class 4, tree diagrams, buying a jacket. The question, in a certain clothing shop, 40% of shoppers try on a jacket whilst browsing. Of those people who try on a jacket, 70% will then go on to buy a jacket. However, 15% of people that look buy a jacket without trying any on. What is the probability that a person who buys a jacket has tried one on? So defining our events, let event A be a customer tries on a jacket. Always define events for our probability questions. So event A, customer tries on a jacket. And then let event B be a customer buys a jacket. The two stages here, customer tries a jacket on, and then they will go on to either buy or not buy. So this is a conditional probability question. What is the probability a person who buys a jacket has tried one on? So just rewriting the conditional probability formula, first of all, you'll find on the Stat 101 webpage, probability of A given B is equal to the probability of A intersection B divided by the probability of B itself. Let's go back to the wording of the question and pick up some probabilities for our events A and B. We're told 40% of shoppers try on a jacket whilst browsing, so our probability of event A will be 0.4. Of those people who try on a jacket, 70% will subsequently purchase a jacket. So the probability of B given A is equal to 0.7. However, 15% will buy a jacket without trying any on. So the probability of B given A complement, B given A complement is 0.15. So in the question we're given probability of B given A, we're looking for the probability of A given B, two very different things. So transferring those values that we've just found onto a tree diagram, we were told that the probability of A was 0.4, the probability of B given A was 0.7, and the probability B given A dash was 0.15. B given that the complement of A has already happened, 0.15. We can then proceed to complete the tree diagram. This sort of question, a very good question for a tree diagram, two-stage process. The two branches, the probabilities must always sum to 1. If we know the probability of A is 0.4, the probability of A complement must be 0.6. Similarly, for each other pair of branches on our tree, probability of B given A is 0.7, so probability B complement given A must be 1 minus 0.7, or 0.3. Looking at the last set of branches, probability of B given A dash is 0.15. These two probabilities must add up to 1. So probability of B complement given A complement is 0.85. Just refreshing our memory with the conditional probability formula. Probability of A given that B has already happened is probability of A intersection B divided by the probability of B itself. Looking at the tree to determine which branches will give us probability of B. Those two paths will both lead us to a total probability of B. considering the first branch, if we multiply going across the tree, remember, this will give us the probability of A intersection B. 0.4 multiplied by that 0.7, or a total probability of 0.28. Completing probability of A dash multiplied by probability of B given A dash, so that's probability of A dash intersection B, will be 0.6 multiplied going across the tree by 0.15, giving us a probability in that case of 0.09. So transferring those figures again, the total probability of B was probability of A intersection B added together to the probability of A complement intersection B, the two paths that both led to that outcome of B. Total probability of B then, 0.28 plus 0.09 equaling 0.37. A, remember, was trying on the jacket and B was buying the jacket, just to refresh our memory. So we want the probability of A given B. Probability of A intersection B on the top line we can pick up from that position in red, 0.28. Remembering to divide by the total probability of B, which we've just calculated at 0.37. So our conditional probability of A given B, works out to be 0.7568. So to complete the question, putting it in context for this problem, just over 75% of people who buy a jacket have tried one on. That's the end of example 4.